previous video, we talked about the definition of compactness for a topological space X. Now we will see some of the properties of compactness for subspaces of a topological space. For this we will need to redefine what compactness means, because now we're talking about subsets. So let's say we have a topological space X and we have a subset Y. We will say that U alpha, this collection of elements in the topology, is a covering of Y if the union of all the U alphas contains Y. So now it's not equal. The definition doesn't change much. It's only that when we were talking about the whole space, this was equal because there was nothing beyond our space X. But now beyond Y, there are other elements in X. So now with this small notation change, let's prove these two theorems. We will prove that every closed subspace of a compact space is compact, and that every compact subspace of a Hausdorff space is also compact. Let's start with the first one. Let's say that we have X, a compact space, and Y, a closed subset of X. We want to prove that Y is compact. So to prove that a space is compact, we have to take covering of that space and prove that there exists a finite subcovering. So we will take U alpha, a covering of Y. This collection of elements has to be in the topology because each of these have to be open sets. And so if we take this collection and we add the set X minus Y, because Y is closed, then we have that this set is open. And so given that this was a covering of Y, now this whole collection is going to be a covering of X. But X is compact. So we know that for this correction, there will exist a finite subcovering of X. Let's call it U alpha I from I equals 1 up to M, and we must have this other one. But now if this is a covering of X, then this family here is a finite subcovering of Y. And like this we have that given any covering of Y, we were able to find a finite subcovering of Y. And this implies that Y is compact, which is what we had to prove. Now let's look at the following theorem. Now we will prove that every compact subspace of a Hausdorff space is closed. For this, let's take X a Hausdorff space and Y a subset of X that is compact. We have to prove that Y is closed, and we will do this by proving that Y is equal to its closure. So first let's make a drawing because it will help us during the proof. Let's say that this is our space X, and here we have our compact space Y. To prove that Y is equal to its closure, what we will do is take an element x0 that is not part of Y and prove that there exists a neighborhood of this element that doesn't intersect Y. So let's actually find this neighborhood. If we take some element Y in Y, obviously Y is different from x0, and because our space X is Hausdorff, we know that we can find a neighborhood of Y and a neighborhood of X that are disjoint. Well, let's call these two neighborhoods UY and BY. So for each Y in Y, we know that these two exist. So these are elements in the topology, disjoint, UI contains x0 and by contains y. And we can do this for each element in y. So if I now grab this other y, let's say y2, there exists one neighborhood here and one neighborhood over there. But we don't know if something like this could happen. For some y, we could have here some neighborhood, but the neighborhood around x0 could intersect our set y. Here it's the intersection. The only thing we know is that this neighborhood of x0 and the neighborhood of y do not intersect. So now let's consider these sets. Given that we have this for each y in our set y, then the set of all the open sets that we can find this way is a covering of y. And y, remember, is compact. So then we know that there exists a finite subcovering, let's call it byi, from I equal to 1 up to m. So if we call B the union of all these sets, this set obviously contains y, but now I need a neighborhood of x0. If I take the union of all these corresponding u's of y's, then, like I said before, it could have non-empty intersection with y. So what I can do instead, because it's a finite amount of sets, u's of y's of I could just take the finite intersection, and that will be an open set that contains x0. So the set u equal to uy1 intersection all of these sets. This set obviously contains x0, and because it's a finite intersection of open sets, then it's also in our topology. And given that uy1 doesn't intersect by1, and the same for each pair of these sets, then we have that u doesn't intersect b. And so if u doesn't intersect b, and b contains y, then u does not intersect y. So I found a neighborhood here around x0, u that doesn't intersect y. Given that x0 was not an element of y, that means that any element that is not part of y is not in the closure of y. And like this, we get that y is equal to its closure. So y is closed. This proof is a bit complicated, but it's very important that we take into consideration this trick right here. This will be very useful for exercises, so it's important that we actually understand what is going on.